It's great. So let's get started, everyone. So let's see. So we have. So today we're going to talk about some kind of review and like some miscellaneous stuff about regression. So if people want to just kind of ask me questions, that's fine. Otherwise, I'm planning to go over some some stuff I think is so kind of cool and so slightly more advanced material that won't necessarily be directly covered on the quiz and stuff, but it will in the process review material that is going to be on the quiz. But if there are other kind of pressing questions you have or examples you want me to go over, I can also do that. So that's the plan for the lecture today. Yeah, so we're the last lecture before fall break. So great. Means about halfway through the semester. You know, you have homework to be out. We went over this a bit. You guys can get started on that. There's also should be probably time to finish it after fall break. I will note that. So just a note again. Let's see. So homework 3 is going to have a little bit more implementation sort of stuff than the first 2 homeworks. Questions 1 and then question 3 are going to be so implementation of first regression and then fairly basic versions of gradient descent. And then we're going to the last lecture in the gradient descent section is going to go over how to solve linear regression with gradient descent, and that you're going to have to then do on homework 4. Okay, you're going to kind of implement, and that'll kind of combine together those 2 parts in homework 3, right? So make sure you understand those 2 parts, and then that'll probably be the most complicated thing you do, but it's very representative of what most of this CPU time in machine learning is doing. So just a preview on that. And then quiz 3 is is today. So we will stop the lecture around 11:35, if not a little bit before. And so at that point the quiz will become available, and I will suggest you take it in here. It will cover actually the previous 4 lectures on everything we've covered so far on linear regression. There might be a little bit on the last lecture from the linear algebra. So as well, again, you'll be able to turn in a sheet, 1 page, 1 side cheat sheet to kind of, I think it's a good way to review for the quiz, and you'll be able to turn that in. So if you haven't prepped that yet, have it on the device you're going to take the quiz on, and you can get up to 5 points of credit. So okay, so that's about where we are. So I can kind of go over the plans stuff, which will kind of be a review, or if there are general questions, I can work with that as well. This is a more flexible lecture. So okay, so I will go with the plan stuff, but feel free to ask some questions. So the first thing I want to review, and this will review and go into the first thing I'm going to talk about. That'll be about kind of an expanded view of what cross-validation is doing. Okay, we'll be talking about polynomial regression. Okay, and this was, remember, this is where we had some input, and we'll say X, Y, and for this lecture, you know, we're going to say that this is R cross R. That means that for each, this is like a set of xi and yi, and each xi is just a scalar value, and each yi is also going to be a scalar value, right? So we can draw the simple picture here, x, y, and you want to kind of, you have some, you know, so some data points, probably with some noise, okay? And you want to fit a polynomial function through here, right? This will be m alpha, and this is a function from x, and it's going to give us a y hat, right? So for every value of x, it's going to map to a value on this curve, and that will correspond with the y hat, right? So okay, so if you remember, so how we solved this, right? What we did is we kind of converted each xi into a a vector, so vi, right? And this is going to be a p plus one dimensional vector, right? So this is called like the Vandermonde transformation, and so this is going to be one xi squared up to xi to the power p. So this is a vector in R, so p plus one, right? And so once we've converted into this vector, we can treat our data as actually being in a p plus one dimensional space, which is very similar to when we had multiple regression, where we had in a p dimensional space, and then we put the coefficient, so just one in front here. Okay, so we can stack these all together into this matrix x tilde p, which is going to be just a stacked version of, say, x1, or sorry, v1, v2 up to vn, right? So this is now a matrix in R. It's n data points times p plus one, so columns, right? And we can solve for then alpha star, the optimal parameters, as x tilde p transpose, x tilde p, this inverse x tilde p transpose, so y, right? This gave us a model where alpha equals to, or alpha star in general equals to alpha 0, alpha 1 up to alpha p, and the model we are trying to fit, alpha star p of x, is just a dot product between alpha star and this, so V matrix, right? Okay.
Is Y matrix or just
so Y is the vector here, right? So yeah, great, good question. This Y is a vector in Rn, right? It's this input vector here. Okay. Yeah. So we have this set of these n items, I equals 1 up to n. Okay. And so once I've created this Vandermonde matrix, I have this vector y, I can solve for alpha star, and this induces this version of this model, right? And then the question of, so then what we talked about with the cross validation is one of the questions we answered with that is, what is the best value p, right? So we can then try a bunch of values p and choose the one which is doing the best on data that we've held out. So before we had done this, we may have split off or held out some of the data, some of the data points, and then we can evaluate that so here, right? So we can do a test train split, right? So what we would do to choose the best P is that we would actually go from X, Y, and we would do a split. So this process is a random split into a X train, Y train, and then a X test and a Y test, right? And so then we can solve for alpha star P, you know, for so various P, and then we can so evaluate the you know, the sum of squared errors on the test data using this model based on P, right? And so then we would choose the P that did best on the data that was held out for evaluation. All right. Okay, so this is a review, and what I want to show is a picture that is sometimes drawn associated with this. Okay, and so this y-axis now is the sum of the squared errors on X. Yeah, so I'm going to say this on, I'll just say on X, Y, on M alpha P. Okay. And so then this is going to be the value P, right? I'm going to put this on the x-axis, right? And so what do we expect to happen is that I'm going to draw two curves now on the training data. As P is smaller, right? If I'm on the training, if I'm evaluating on the training data, as P is smaller, the error is going to be larger. And as P gets larger, I'm going to fit closer and closer to the data, right? So the error I measured, the sum of squared errors, which is the cost function I'm trying to optimize, is going to decrease with P, right? I'm going to fit the data better and better. I have more powerful functions. So the first curve I'm going to see is that this curve is going to go down, and then at some point after here, it's this curve is going to be 0. Okay, so this is the sum of the squared errors on X train and Y train with respect to M alpha P. Okay. Right, and so at some point, where is it getting to 0? This is where P is equal to N train, right? The number of training points. When P is equal to the number of training points, then I should be able to get 0 error. The polynomial should be able to fit through every point so exactly, up to like numerical error, okay? And so this is the training picture. What's the test picture going to look like? Okay, so if I were to draw the same thing, but I want to evaluate on the test data instead of the training data, right? So it's gonna, so at the first point, it's probably going to be slightly larger, okay, for any value like P, you know, say P equals to 1, right? So just a linear function. It's probably going to be slightly larger on the test data than on the training data, okay? Right, because I solved the optimal on the test data, on the training data. So on the test data, it probably is not quite the optimal, so slightly larger. And then it's going to come down and stay above this curve, right? It's going to come down like this, okay? And at some point, I'm going to start fitting the data a bit better than I actually should. I'm going to kind of like overfit onto the data, right? And so it's going to start coming, it's going to plateau and then start coming back up, right? So it's going to maybe not this far back up. but I'll start coming back up again, okay? And so typically, you know, what I'm telling you in the most common situation where you have, you know, you've got a reasonable amount of data, is you want to identify this point in the evaluation score on the yeah. So this is on this is now the curve here on the sum of the squared errors on X test, Y test, M alpha P. Okay, so this is the sum of squared errors here. And so on this curve, I want to find the minimum here, and this is saying, okay, this is how I expect to generalize onto some new data that I haven't seen before, and then this would be kind of the right value of P to choose. Yeah. In this case, it's actually going to be discrete here. Yeah, we're going to do discrete P. There are other situations where you do something very similar, where you have, you know, in machine learning for classification, other types of regressions, you're going to have these hyperparameters that you're not going to know necessarily how to easily solve for, like the alpha parameters. And those might be so continuous, and then you might have a continuous function here. But for now, I'll just draw it as a continuous curve, just in, you know, so intuitively here. Yeah. So, okay, and so this tells you, okay, this is probably the best value of P, and this is what you should choose. That will work. You expect to work the best on new data. That's what this green curve is explaining here. Okay, now I'm going to tell you something slightly so different. There's this kind of special point here where you're so basically interpolating. Most people will stop these curves, you know, here. They say once it starts going back up, I probably don't need to kind of evaluate this anymore. Fitting something with as many parameters as I have data points seems like, you know, so silly, not very robust to noise. And for a long time, the story kind of ended around here. Recently, with people observe this phenomena with other models, especially ones using things like deep learning, where the number of parameters, P is kind of like the number of parameters here. Number of parameters became much bigger than the number of data points you have. Often you have a huge number of data points, like 100,000 data points, but you might have more parameters than that. These are really complicated models. And what seemed to be happening here, it's pretty interesting, is that when these deep learning models are doing better than just polynomial regression. And basically what's happening is that this curve came back down again. Okay, so as P, the number of parameters got larger, this curve started going back down again, and sometimes lower than this value. Okay, that we found when the number of parameters was less than the number of data points. Yeah.
What value feel like in the hundreds or like millions?
Yeah, so I mean, it depends on the problem, right? And so this does not always work. It typically works when you should think about having, there's some sort of underlying function that is describing what's going on, and you should have well more than enough data to understand that function, right? So you think there's a function with noise, and if there is like a third degree polynomial, you could, if you had like 3 or 4 data points and there was no noise, you could find the exact function. But if you have a little bit of noise and you have 1 million data points, well, then you really understand that function very well, way more than you need to describe the underlying function. You probably don't even need 1 million. I'll show you an example, I think, with 20 data points in a third degree polynomial where this kind of works. Okay, and this model starts doing a little bit better than this model here in some cases. Okay, it's sometimes if there's more noise, it's kind of things start acting sort of, there's this phenomena starts happening. There's a couple of things that this won't be explicit in the example. I'm gonna show an example on Collab where you actually see this happening. But so oftentimes what you need to do is actually optimize, say that alpha star is going to be the arg min, say, of alpha, where the cost function has two components. One is the sum of the squared errors on x, y, m alpha, right? But there's also this other term that looks often so something like this. What this doing is it's putting a norm on alpha, and I want that to be small. And I have some coefficient in front here called like a regularization term, and I can set this quite small often. So in this case, maybe this might be 1/100. So it's pretty small, but what this term is doing is it's biasing towards functions which have smaller coefficients, and then they're going to be simpler. And this shows up in a variety of ways. This is the simplest way to see it, that I want to bias my optimal thing, not just to have a small error, but also to be simple in some way. This shows up in like gradient descent, deep learning sort of things. In other ways, like if you start your guess as an all zero thing, then it will tend to find a solution near all zeros. And so there are other ways that this kind of shows up. But sometimes you need something to kind of bias a little bit towards a function which is simpler. Okay. Okay. So this is called, like the, double descent curve, where it's kind of, you're seeing this curve coming down first on the testing data, and then past the interpolation threshold, where you're interpolating the data. There's basically one solution here that can interpolate the data, but here there are many ways to interpolate the data on the training data, and and if you bias towards a simpler solution, it'll interpolate the training data and find something simpler from a much more complex family of functions. Okay, yeah.
So is it true that will this curve ever go back up as you set parameters, or just continue to go down?
Yeah, there probably are cases where it might start to go back up just because it's maybe too complicated. If you have so many parameters, it might be too hard to solve. One of the issues that isn't the case for what we'll talk about in this class, where all the functions will be convex, which will make them nice. In deep learning models, for instance, they often aren't. The models may not have convexity. So we'll see that ensures that we'll be able to find a good solution. And then you may have an issue where the problem is so complicated, I can't find a good solution for other reasons. And there might be other factors that are going in here. But in principle, it shouldn't need to go back up again. But there may be, in practice, you may see it going back up for other reasons. But typically, you kind of just see it going down. These often get very expensive to work, right? This is also much more efficient to work with, and this becomes more expensive. So people often probably stop before it gets too expensive. That might be more of a constraint. Yeah.
And I want to backtrack a little bit.
Yep.
For those peak dots, the peak dot on the green graph, that's lining up to the value you want for P. That's the minimized access.
Yeah, that's the minimization of the sum of the squared errors on the testing data from the model you found on the training data, right? Yeah.
And then if we were to, so there are two things we can do with the SSA. We can choose the correct P and then estimate how our data. If we want to estimate how our model would get a different SSE for both the training.
Yeah, right. So if you want to estimate how well it did new data, you would then have to hold out a third set of your data, and then you would choose this value of P, So then your training is learning alpha from the training data, P from the testing data, and together alpha and P is what's making the model. And then you have a third set, an evaluation set, or different nomenclature for this. And that's what you use to say, estimate how much error I expect to see on some new data. Yeah. Okay. Oh, yep.
So is it possible that, like, past that line that you're overfitting to the testing data, like if you were to check on the validation data, that it would, like if you were to do another line, it would go back up again?
Yeah. So the that probably should not happen here. You might get a little bit of that, right? If this might be, maybe this is kind of bumpy going down, or this function is actually bumpier. It doesn't need to be a smooth function. And so, for instance, there might have been like 3 values. What's more common is there might be like 3 values along here that all about the same minimum. And the one you chose with P might be slightly, like P equals 4 might be slightly lower than P equals 3. But then on the evaluation data that you held out, maybe P equals 3 performs slightly better. But the model, the alpha you chose, does not look at the testing data, right? So the alpha should, think of this green curve. Remember, there's kind of like you should think of it kind of like there's noise on this green curve because it's a random sample, right? It's a random sample from the full distribution. And so I'm estimating this green curve. And so I've got actually some tail bounds, some concentration of measure estimate on here. And so I don't know the exact value here, but I have an estimate of that value. And so I might be slightly off in that estimate. And if I redid this with different evaluation data, I might get slightly different. And so which one is the minimum on one might not be the minimum on the other, but they should be pretty close. Okay, but the choice of the alpha did not look at the green data, so it shouldn't affect it too much. It's more in the space of random error. And so you may have chosen something slightly wrong because of that random error, but it won't be significantly wrong on the evaluation. Okay, here, let me try and show this in this really cool demo. This is not one I made, but I found this. There are a number of things online that I've kind of found how to demonstrate this, and this is the one I think is the most clear and shows this on polynomial regression. They chose some random seed that makes this example work well, and that random seed was used to choose data. We're going to choose n 20 data points, and they're going to fit, the data is going to be according to a cubic curve, so a 3rd degree polynomial on some sort of range here, and then they're going to add some noise onto the actual data. And that seed happened to make this example work pretty well. And they're going to represent the polynomial in a slightly different basis that will make things slightly more stable. And I'm not going to kind of go into this, but they didn't. I think they don't use the Vandermonde. They use a different expansion of the polynomial, which is slightly more stable, and that's why this. And there are a couple other things that they do in here that makes this slightly more stable, but the math is more complicated, so we're not going to worry about it in this class. But they build this widget, okay? And so what this should look like here is let's see, the data is the red data, the ground truth is the blue curve, right? And then they fit the I think so, some fraction, like 30% of the data is given noise and 70% is directly on the curve. I think it's how they generated this. And then they fit in this case, a 19 degree polynomial, right? You can, in this widget, allows you to say, let's do 8 instead. And now it I put my keyboard on here so we can see this a little bit more easy, hopefully. And so it's refitting this curve, right? So if I use 8, this looks pretty reasonable, right? It should actually be, they have some examples here, right? This is 20, right? So it's pretty much, it's overfitting. It's going through all of the data, right? But the curve is very wild, right? So this seems like not very good. This is the answer with 3. This is basically the right answer here, right? So it's not exactly the blue curve either, right? It's because there was some noise, the orange curve is slightly worse than the blue curve. I'm not getting exactly 0 error, even though that's pretty much the right model here. And this is with 1,000, okay? So 1920, it was going crazy. At 1,000, this weird thing is happening where it's interpolating through all of the data points. And it can interpolate all of them. There are many ways it can do that. And it shows this one. This is the kind of a simplest way it can interpolate it, all the data points. And when it's not interpolating, it kind of goes close to where the actual model is. It's not varying very far away. Okay. So kind of strange, right? So this doesn't necessarily give better error. I bet in this case, this didn't exactly illustrate what I was going to show. Where if I tried to, if I computed the error, the cubic should probably do so better here, right? On new data, but so maybe not, right? If there was some structure to this noise a little bit where it came off the cubic, maybe this one does slightly better. Right, because 30% of the data had noise. Yeah, so kind of this phenomena happens. I think that was 1,000. I think it happens around 100. Yeah, so at 100, yeah, let's look at 100. It's not quite as smooth, but it's actually coming pretty close to the blue line, except when it is deviating, right? So it's kind of a strange phenomena. This is something people didn't realize until the last, like 5 years or so. So it's caused people to rethink what is the right way to do cross-validation. Should you have more parameters than you have data points? Maybe it's not so bad to have more parameters than data points. If I had, 10 years ago, if you had said more parameters than data points, that seems like a very bad idea. Right. Now it's like, okay, maybe this is okay.
Can these things like run on like laptops? These like a million.
Yeah. So it's computing it on Google's server on Colab, but it's not. You have 1,000. At some point, you have to invert 1,000 by 1,000 matrix. You have to multiply 1,000 by 1,000, or you have 1,000 by 20 matrices together to get 1,000 by 1,000 matrix, and then you have to do like an inversion of that, and that's definitely something you can do on a laptop. We will actually. How do you compute the inverse of a matrix? I kind of said you can do it in Python, right? We'll actually see an algorithm how to do that. So later in the semester. And you'll see that, okay, it's not so bad. It's something you could implement. These are more stable ways of computing. They use a pseudo inverse, which is a slightly more stable way of computing the inverse, and we'll basically see how to do something like the like the pseudo inverse. The matrix, the 1,000 by 1,000 matrix, is not going to be so full rank. Okay, so if I go back here, right, and I solve this, remember, and I had to, alpha star was this x tilde p transpose x tilde p. This is going to be p plus 1 times p plus 1 matrix, but it's going to be made up of only n items. So the rank of this is going to be at most n. So if p is larger than n, that's can't be full rank. The rank is going to be at most the number of data points. So I can't technically take the inverse here. So I'll have to solve this in a different way. One way will be gradient descent, which we'll see later in the after break, which is going to work. There are other ways of computing something called the pseudo inverse, which you can also do in this case, and it will give you a solution. Okay, so there are some like technical details about how to actually get this to work, but this is kind of a neat and a newer perspective on cross-validation. Okay, cool. So is this, I thought this was kind of neat and would share this when I had an extra space in the lecture. Okay, any other, thanks for the great questions on this. Okay, I was hoping for the next 15 minutes, maybe 13 minutes or so, to try and answer a little bit more in depth of why you would do alpha star equals to X transpose X inverse X transpose Y. Why? This gives me the optimal sum of squared errors. Okay, and we can give a little insight into this, and I'll probably kind of tailor how far we go into this based on, how much time we have. Okay, sounds interesting. There's a geometric interpretation I probably won't get to. It's kind of explain the book. There's parts of this proof which I think, or this argument, why I think you should mostly be able to follow. And part of it, we start looking in, you have data in D dimensions, but you have to think in n-dimensional space, which gets a little bit kind of confusing. And so we'll go through it, and if it doesn't all make sense, hopefully you get the main idea of why this is the case, at least. Right. So, okay. And I'm not using the tilde here. This is for like a D-dimensional setting. And I assume like maybe it already has a 1 in the first column. Okay. Just to make the notation a bit so simpler. Okay. And so remember we're going to consider the sum of squared errors of X, Y, M alpha here. And remember, this is equal to I equals 1 up to n of the residual squared, which is I equals 1 for n data points of yi minus, so some model alpha xi quantity squared. Right, so this was what we're optimizing, and what's I think neat about what we're going to think about is that this is a function of alpha. Okay, because this X and Y and the structure of the model here are going to be so fixed. The only thing that's variable here is the choice of alpha. So we're going to think of this now as a function of alpha, and and how do we know if alpha is the optimal of a function? Right? There's going to be something like this S alpha here, and there's going to be a function, maybe it's not 0, but like there's some function, and I want to find the minimum in the space of alpha here, right? Alpha is an RD, let's say RD plus 1, RD, just say RD, okay? And I want to find that minimum value of alpha, and how do I know if the function is at, so the minimum, that's if the derivative of the function is equal to 0, okay? If first derivative is equal to 0, and we'll talk a little bit more about derivatives and minimums and stuff in the section after, so after fall break. What so this is kind of a preview of that as well. But what's tricky is alpha is an RD, so I don't just have kind of one minimum here, but it's multidimensional. So I have multiple partial derivatives, and I need all of the partial derivatives to be 0. So if I can take the partial derivatives and set them all to 0 and then solve for alpha, well, that gives me alpha star, assuming some convexity and stuff that, again, we'll talk about after fall break. Okay, so some of these tools we will review why this is the right solution after the fall break, but I'll kind of go through the mechanics here. But one thing, so this is kind of a complicated function by itself here. So I want to start by thinking about just the function of the residual, right? So this S alpha is a function of these sum of the squared residuals. So I want to say, what is what's useful here is going to be the partial derivative of the ith residual with respect to alpha j, the jth coordinate of A. Okay, so so this will be something I'll need to calculate. If you remember, the residual I is yi minus alpha xi, right? And so this term here is actually a sum j equals 1 up to d of alpha j xij, right? So that's actually what the dot product is doing. Okay, so that means if I were to take the partial derivative with respect to alpha j, it's just one term in that sum, right? The partial derivative here is just going to be negative xij, right? That's in this matrix of inputs, the big X, right? That's the ith row in the jth column, that value, and the negative of that. The negative, it turns out, won't matter so much here. Okay, but it's the negative of that value. Okay, so this is the partial derivative of the ith residual with respect to the jth coordinate. Okay, and so now what I want to do is I want to set 0. I want to set the partial derivative of this whole function of alpha with respect to alpha j equal to 0, right? So now I can use the rule of partial derivatives, and this step is a little bit unintuitive, so why you choose to do it this way, but the math works out simpler. You can do the partial derivative of this this is from kind of this form of it right here, right, is equal to Ri times the partial derivative of dRi over d alpha j. Okay, and there are two there are two versions of this. So it's squared, so you bring the 2 in front here. Okay, the 2 will cancel out because it'll be equal to 0. Okay, and so now I can substitute this as 2 sum equals I equals 1 up to n Ri negative xij, right? Because I solve for that partial derivative above. Okay, and so then I can write out the definition of, so the residual, right? And this is yi minus alpha xi minus xij. Okay, so this is my partial derivative with respect to j that I need to set equal to 0. And I need to set this to 0 for all values of j, then I will guarantee I'm at the minimum of that function. In no direction j can I move in a direction that is changing, right? So now I just basically need to solve for alpha here, right? But I need to solve for alpha with respect to all the equations at once. So I need to now set up a system of equations here. And these are called, so the normal equations. And why it's called the normal equations is because of a picture in n-dimensional space that I may or may not actually get to explain. But so you can rewrite this as sum. So I'm basically going to set this term equal to 0, and there's a minus in here. This is yi, minus this dot product, and I can push through that xij through this on both sides here. And so I'm going to get xi equals 1 up to n. Xij, I can multiply it on the left multiplied, it's a scalar value, times xi alpha, and this should be equal to the sum equals I equals 1 to n for xij, so yi, right? So that's this on this negative side, I added this term to both sides, to the 0, right, onto the 0 side, and so I get this equation here. And this is true for all j equals 1 up through d, right? So this is true for all, I need this to be true for all values of j. And so then I can set this up, and this step is a little bit hard to see, but I'm going to push this xij, the sum, into the inner product here. Okay, and I'm going to write this as a vector, and it turns out, I'll just kind of write this up, and then we'll probably look at it a little bit and then stop. But I can write this as x transpose x. This is the full matrix x times alpha. I've kind of just changed the order of operations, but that's fine. So I multiply these first times alpha, and this should be equal to x transpose y. Okay, because now I've done this for all values of j. So kind of this yi, which was a single value, turns into, I'm now over the sum. Yeah, I'm multiplying this over the sum, and I get this for everything in the matrix for all values of j. I've got this system of equations here. And now solving for alpha should be fairly straightforward. I just need to divide by this term on both sides, right? How do you divide? This is a matrix. How do you divide by a matrix? You take its inverse. So I left multiply by its inverse on both sides, and this leads to alpha is equal to x transpose x inverse, right? If I multiplied kind of x transpose x inverse here, then these would cancel with each other, right? So then this is x transpose y, right? And so that's how I get this solution here. Okay, there are a couple of steps in here that are a bit kind of a little tricky to see because I've got a system of equations and I kind of wrote them up kind of quickly here, but this is basically how the proof goes. So now you kind of get a sense of why this is the right solution, but it's kind of, linear algebra is a little bit hard to kind of think about if you haven't seen this before. So great. So I will stop here so you have time to kind of clear your mind for the quiz, which should be about to open. Okay, so good luck on the quiz, everyone. We'll have it quiet in this room. If you have a question for me, maybe you can pull me out in the hallway, and I'll see you after fall break otherwise. We'll start gradient descent.